Okay, this is problem 513. Get a pen here real quick. What we want to do here again is determine what the torques are between each one of these, between A and B, B and C and D. Again, if you want, you can just draw yourself a straight line. So 15 kilonewton meters between A and B, that's not going to change. So if it's turning this way, this beam is going to, or the shaft has to resist it. So what you can do is just come up here. So we'll let this be A. We'll let this be B. And I'm just going to put the value of 15 right here. Alright, now it's going to jump up another 30. So let me move this up over a little bit so we can get that. Just do it like that. Sorry. And we're going to go up another 30. So 30 plus 15, that gives me 45. Jump up to here, and this is going to go all the way over to ICC. So this is going to be C right here, and again that value is going to be 45. Alright, the reason being because both these go in the same direction. So now when I hit C, it's gone back. I got to subtract 75 because both these go in this way, and then this way. So 45 minus 75 is going to give me a negative 35. So drop all the way down. Get a line here. I'm going to go over. And I'm going to extend this line out a little bit longer. And we'll see. So we said that's going to be minus 30. Alright, and then we're going to come all the way over, and we got what? Jump back, because we know we have to return back to 0. That's a good way to check to make sure you haven't made mistakes, is we'll jump back to 0. Alright, so what you want to look for here is to determine what is the maximum torque. Well, the maximum torque is going to occur in the beam anywhere between B and C. So this area right in here is where you're going to get maximum torque. And obviously you're going to get maximum shear. So all we have to do to solve this problem is we know our allowable, so we'll put our equation that shear stress is going to equal to torque times the radius over J, polar moment inertia. So we'll put in our values. We got 85. We got megapascal, so we'll make that times 10 to the 6th. We'll set that equal to our torque, which in this case will be 45 kilonewton meters. So put 45 times 10 to the 3rd. And now you have to multiply it by the outer radius. And this shaft has 1.5, so it'd be 75 millimeters, or 0.075. And then all we have to do is divide by the polar moment inertia. Again, it's hollow, and the hollow is always going to be this, pi over 2 times outer radius squared minus inner radius squared. I'm sorry, fourth power. So we'll put in what we know. The outer radius we said was 0.075. And we're going to just solve for the inner radius to the 4th power. Alright, so what we can do is bring this all the way up. Pi squared still down here. And then we'll bring this down to here. And just bring the 85 down. Oops, sorry. Change that color. and that's times 10 to the 6th. Okay, now what we should do, we need to bring this back over, so I'm subtract that from both sides. Which eliminates it from this side. Now we get, oops. Okay, I'll just mark it out. So eliminates it from this side. Now we got to get rid of the negative, so we're going to multiply everything by negative. That gives me negative here, a plus here, and that gives me plus here. Now we got to get rid of the fourth, so I'll rewrite how we're going to do that. We could say R1 is going to equal to the of all this to the 1/4 power of, and I'll move this over to the front. Run that numbers, and I believe you get 0.0. Let me think what that number was. That was 0.5022 millimeters. Scroll down. So that's the same thing as 50.22 millimeters. Again, that's your inner radius. So all you have to do to find the thickness is take your outer radius, which was 75, subtract 50.22, and you're left with a value of approximately 25 millimeters. So that problem is really not bad at all. Again, the critical thing, and again, this is not hard, is determining what the torques are at each location here. But again, just work through it between points, between A and B, between B and C and D, and you'll get this problem. All right, best of luck.